Good? So, yeah, we should. Yeah, I think. Yeah, I think is it better this way? You can sleep better if it's dark. So hello everyone. My name is Barnabás Pócos, and this is lecture 2. And in this lecture and in the next lecture, I will talk about linear programs, how to solve them, and what they are. So first, administrative questions we need to discuss. This is the most important one. That please ask questions whenever you don't understand something is confusing, then don't hesitate to ask. Okay? Second point, Ryan already told you that the lecture, there will be 40 minutes part and then 5 minutes break and then 30 minutes part. And if I was right, I set up my alarm clock so it will warn us when I should stop. And the slides can be downloaded from here. And I will try to upload the slides before the lecture, so you can just print them out and bring it here. That might help your life a little bit. Second, another point is that next week there will be an anonymous feedback survey on Blackboard, and please use it. So if you don't like something, tell us that there. If you like something, you can tell us that there too. I think it's important that if you don't like something, then you should tell us as soon as possible. So it doesn't make sense to complain about something at the end of the semester, right? So then we can change things. And the other thing is subscribe for scribing. Ryan already told you about this, right? So you know what this is. Okay, and finally, my office hour is after this class. So if you have questions, we can just walk to my office and discuss your questions there. So we will start with some basic definitions that we will need to define linear programs. And first thing is that what will be our goal? We want to minimize the function f of x, right, or maximize function f of x, and we want to discuss more and more complicated problems. So what's the simplest possible function you can think of that we need to minimize? So tell me a function. Quadratic simpler function. Think about the title of this. Linear, okay. Or an even simpler function, constant function, right? But doesn't make much sense, but right, it's pretty trivial. So we can think of constant functions. Fx is c, and the minimum is c, maximum is c. So second, more complicated, is a linear function, say ax plus b. That's f of x. What's the minimum of this? I hope you can solve this. So x can be any real number. What's the minimum of this? Minus infinity, good. What's the maximum of this? Very good. Okay, let's move on. What if I have bounds? So let's say this is f of x, ax plus b, and I know that x should be between c and d. What's the minimum of this function? Minimum point? C, maximum point D, right, if A is non-negative. Okay, so we are good with linear functions. So let's move on. And let's discuss n-dimensional linear functions. So then our cost function is c1 x1 plus c2 x2 plus dot 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 cn xn. And we can have constraints as well. So subject to a11 x1 plus a12 x2 a1n xn. This is say less than b1, and I can have m constraints. So a m1 x1 plus a m2 x2 plus a mn xn is bm, right? And we can have constraints on the bounds too. So say L1 is less or equal than x1, and x1 is upper bounded by u1. And we have n variables, so ln xn u1. Oops, yes. So, and of course these bounds L, I, it can be say minus infinity or plus infinity too. Is this definition clear? Right? So we want to discuss in this lecture and next lecture how to solve these linear programs. Okay, I can write the previous problem using matrix and vector notations too, right? And then in that case, the cost function is just C transpose X, where X is an n-dimensional Euclidean space. And the constraints, I can just write with matrix notations like this, that AX is less or equal than B, where B is a vector and A is a matrix. And you can think of vector L and vector U as well, where they are in the n-dimensional Euclidean space.
You want to switch the dimension with
Yes, I want to. Okay, I'm lazy. Okay. So that's clear so far, right? Questions? Oh, very good. And so an example, so say we want to minimize, say this function, minus 2x1 minus x2 subject to whatever we want. Okay, and if I want, I can rewrite this whole thing with matrix notation too. So please help me. What's C vector in this case? Minus to minus 1. Minus 1. Okay, we need a vector B. You want it transpose? Yes. Vector B. Transpose. And matrix A. I cannot hear you well, sorry. 1, 1, 2, 3. Cool. So we know this. Okay, so the goal of this and next lecture will be to solve these kind of problems, and we will discuss an algorithm for that. That's called the simplex algorithm, which will have to fit. Yes.
Going back to the previous slide, is there any reason to distinguish between constraints and bounds? Couldn't you write all those bounds?
A very good point. So just to define the problem, there's no difference, right? But for the algorithm that we will use, it will be important that we will use these constraints. X1 and X2, they will always be non-negative. So you will start with the linear programs where you might have different constraints, but we will see how to transform the linear programs to this form where we will have these kind of constraints, and we can run the simplex algorithm that requires these non-negative constraints on the variables. Is it clear? Good. Okay, later we will see other algorithms too when we discuss interior point methods. The other goal of these lectures are to understand why linear problems are useful. So we will see some motivating examples and applications in machine learning. I chose machine learning because I'm from that department, so it's a selfish choice, but I hope you will like the example there. And we also need to understand the difficulties. So how difficult are these problems that we just discussed, these linear programs? So the algorithm that we will propose, will it converge or won't? How many operations we need to solve the problem? So is it polynomial in the size of the problem or exponential? And will the algorithms find the exact solutions or they just approximate it? So we need to understand these questions, and we want to answer all of them. Is it clear so far? Okay, so this is the table of contents. So I will talk about a classification problem in machine learning and how to describe a classification problem as a linear program. And we will discuss different forms of linear programs, such as the standard form and canonical form. We need to define these terms here, such as basic solution, feasible solution, optimal solution, degenerate solution, and finally we will discuss this simplex algorithm. Okay, so the goal of this lecture and the next lecture is clear so far. Good. So let's see some in this block some motivating examples and a little bit of the history of linear programs, and then we will sketch a linear program. Okay, so the whole story started around 1947 when Danzig proposed the simplex algorithm. And according to a leading computer science journal, this is one of the top 10 algorithms of the 20th century. So even though you might never use it, you should know it. The theory of linear programs, they were motivated by problems in World War II. There were problems there like job scheduling. So for example, you wanted to assign 70 men to 70 jobs where we had some constraints that each job has to be done with someone. There might be some ordering between the jobs and so on. Another problem that was pretty common those years is a blending problem. Say your goal is to produce a blend that contains 30% lead, 30% zinc, 40% tin, and you can buy, say, 9 different alloys that contains different percentage of these material, and you want to blend them in such a way that the final blend will contain this percentage of these materials, and these 9 different alloys, they might have different costs as well. So you want to purchase some quantity in such a way that in your final blend you will have these percentages of the different materials, and you want to produce this using having minimal cost. Other problems are, say, network flow optimization, where you want to transport some material from one point to another point, and you can choose different routes and how to solve that in an optimal way, where the routes might have some capacity, so you cannot send more material on one route than its capacity. Okay, well, here is another concrete example. Say you have a furniture company that manufactures 4 models of desks, and each desk, to produce a desk, you have to ship it to a carpentry shop and then to a finishing shop. And each desk requires some man hours on labor. So for example, desk 1 requires 4 hours in the carpentry shop, then 1 hour finishing. And it can make you $12 profit. Similarly, say desk 2, it needs 9 hours to be in the carpentry shop, and then 1 hour in the finishing shop, but it can make you $20 profit. And you have overall constraints that in the carpentry shop you cannot spend more than 6,000 hours, and in the finishing shop you cannot spend more than 4,000 hours. The question is how many desk 1, desk 2, desk 3, desk 4 to produce in order to maximize your profit. Is it clear? Okay, and the solution is this, that of course we will have, so we will produce X1, X2, X3, X4, not this much, so X4 desks. And the maximum profit would be 12 times X1 plus 20 times X2 plus 18 times X3 plus 40 times X4. Right? So this is what you want to maximize. And of course you have these constraints that the linear combinations of 4, 9, 7, and 10, just forget X5 is less than 6,000, and X1 plus X3 plus 3X3 plus 40X4 is less than 4,000. So why do I have that X5 and X6 is there? Any guess why I made this mistake? Yeah, they are slack variables. Actually, so the original problem is this is less than 6,000, 4,000, and I got confused, so I write X5 here, X6 here, and then it should be equal to 6,000 and 4,000. Okay, so apart from this confusion, the problem is clear, right? Question? No? Clear? If something is not clear, do this, or raise your hand, or your guy next to you, his hand, or so somehow tell me if something is confusing. Okay, so here is my question. Why is it called linear programming? Why is it called linear? But why is it programming? Right? That's my question. Is it similar to programming? Answers? Someone guess? Or it's trivial value programming? So I just saw values for linear programming when I first learned linear programming. So one is that those years they use the programming in a different context, in scheduling, and linear programming can be used for scheduling programming. That's one. It's not that excellent, I would say. Second is that those years computers got more and more popular, and it was easier to get grants if you wrote the type of program. Because then the DARPA and US Air Force give you more. So I don't know, you can choose which one you believe, but these are the two explanations that I get. Okay, so why we like linear programming? Because probably this is the simplest non-trivial optimization problem, we can think of. And many complex systems, even if they are not linear, they can be well approximated with linear equations. And then linear program can approximate the solutions. There are many important applications, and there are efficient toolboxes that can solve huge linear programs. So let's see. Sketching a linear program. So here is an example. We want to minimize in x minus 2x1 minus x2, and I denote the cost function with z. And we have constraints such as x1 plus x2 is not bigger than 5, 2x1 plus 3x2 is not bigger than 12. We have constraints that x1 is not bigger than 4, and x1 and x2, they are non-negative. So here is a coordinate system, and let's see what happens. So this is x1, that one is x2, some ticks. And this is my cost function, minus 2x1 minus x2 is z. So this is what we want to minimize. And you can observe that let's discuss it later. So first, let's see the equation. So say x1 is 4, so this is just this line here. We have another inequality, that's x1 plus x2 is lesser or equal than 5, so I'll draw this equation. And finally, the second constraint is that 2x1 plus 3x2 is less or equal than 12. Okay, so we have these constraints. That's clear so far, right? And now the question is, if I want to minimize this, where to push this such that it will have a minimum value in z. Okay. Some definition, this domain here is called feasible set. So those points that satisfy these constraints, they are feasible. And we can also observe that this object has 1, 2, 3, 4, 5 corners. I can denote this with O and then A, B, C, D, the other corners. And any guess, if I want to solve this optimization problem, where would be the optimum? What would happen? So what happens if I change z, then this gets shifted, right? And we need to shift this somewhere where it's still feasible, but it's maximally shifted. So where will be that? Yeah, it will be in C, right? So it's very crucial that you should see this. If you cannot see this, then tell me now, otherwise you will have difficulties later. Okay, and so this is optimum. The optimum is at C. And you can just read the optimal solution is x1 star is 4, x2 star is 1, and you can calculate the z value of c star using this equation, and that will be minus 1. Okay? So a few more definitions, that these points inside, we call them, so these are the feasible points, but they are also suboptimal because they are not optimum. And inside of these constraints, there are no active, inside of this region, there are no active constraints. And say on an edge, there's one active constraint, and in a corner, there are two active constraints, right? Both of these are active. Okay. So what the simplex algorithm will do, we will see that it starts from a feasible point, say from here, and it jumps on the corners till it finds the optimal solution. So we will be able to prove that the optimal solution is always in corners. And then the simplex algorithm will just jump from one corner to a neighboring one till it finds the optimal solution. And it might jump this way too, depends on what kind of variant of the simplex algorithm you use. Any question so far with this? It's clear? Good. Okay, so some difficulties is that first the feasible set might not exist. So it might happen that the equations, they contradict to each other and then there's no feasible point. The other difficulties is that there might be infinite many global optimum. So for example, if a whole edge contains the global optimum, so it's not a corner then. And depending on the system you want to solve, the infimum can be minus infinity or plus infinity. So we need an algorithm that can handle all these problems. Question? Yeah. Oh, I just meant that you mean this, that optical infinite many global. That the global optimum is not a single point, but the whole edge. Right? So for example, if the cost function is parallel to one of these edges, then I could, and the whole edge would be global. Clear now? Okay, so let's see application. And the application we will discuss is how to do pattern classification using linear algorithm. So if you are you want to see more information, more details about this, then you can look at these slides here. And our goal is now to show that linear programming can be used for solving linear classification. Why would you ever use LPs? Is the only reason is that there are efficient LP solvers. So you can use them to solve huge classification problems. So our formal goal is that given two sets, one is H contains vectors H1, H2, HH in the n-dimensional Euclidean space, and we have another set, say M, M1, M2, MM points, right? So we have these two sets, and the first problem is to determine whether H and M, they are linearly separable. And the second problem is if they are linearly separable, then we want to find a separating hyperplane. So here is an example for a linearly separable set. So say this is H, this is M, and we want to find this line here. And it is an example for a linearly not separable set. So you cannot put a line between the red and blue points that would separate these sets. Okay, so the first observation is very trivial. I'm just saying that H and M, they are linearly separable if and only if there exists vector A in the n-dimensional Euclidean space and the B real number such that H is a subset of those x points in the Euclidean n-dimensional Euclidean space with which A transpose X is, say, bigger than B, and M is a subset of these points where A transpose X is not bigger than B. Is it clear? So this is just the definition of what it means linearly separable. Right? Good. And our first lemma, is this, that let H and M be these two sets, and we are saying that they are linearly separable if and only if there exists A in the n-dimensional Euclidean space and B real number such that, and now comes the tricky part, A transpose H I minus B, I'm saying that it's bigger than +1 for all points in this set, and for the other set, using the M points, this is less than -1 for G. So let these sets be strictly separable. Then what I'm saying that I can rescale, I can find A and B such that I can write this +1 here and this -1 here. Okay, so the linear, just the definition that they are linearly separable, it doesn't mean that I could find the +1 and -1. We need to prove that. Right, so one side is trivial, that if this direction, this is trivial. If there exists H and B with this property, then of course that's linearly separable, but we need to prove this other direction too. Ideas how to prove it, or you can see it, or how difficult is it to prove? So for example, if it's a midterm question, then you would be very mad or super happy. The problem is clear, and is it difficult or easy, or we don't know? Yes. Yeah, so what we know is that we have, say, H and M, they are linearly separable, so it means that there's a vector, say, C and D such that C transpose X plus D will separate these two sets. And we need to find, using this C and D, A and B, so that they can be together. Yes. 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 Yeah. And what with the minus one? Yeah. So yeah, that's one way to do it. Okay, so what we know, what we just discussed is, so from the definition we know that there exists, I use C and D such that C transpose X is always bigger than B, and when the points are in H, and C transpose X is not bigger than B when the points are in M. And we need to find an A and B. And I'm just saying that let's say P number defined such that this is the minimum of C transpose X minus when X is in H, and maximum of C transpose X when X is in M. Right? So what do we know about this difference? So I know that the minimum C transpose X, when X is in H, it will be bigger than B, right? The maximum when we are in set M, it will be less than B. So I know that this is never negative, right? Okay. Yes, it can be 0 too. So if they are strictly separable, it cannot be 0. If they are not strictly separable, then it could be 0, right? Oh, okay. So you mean that definition? Oh, I cannot hear it. Last slide. This one? This one? This one? So what I want is that this is bigger than 0. That's okay? Good. Clear? Now we are good. Okay. So let's move on. If I can move on. Okay, so we have this. And we have to have 5 minutes break now. So then we will continue, okay? In the break, you can think about the rest of the solution.
We define this if it is strictly bigger than 0. So it cannot be from the definition. From the definition, you said when they are separable, the CTX is bigger than B, but the CTX if X belongs to M is smaller or equal to
Yeah,
B.
so I meant it cannot be equal for that.
Yeah,
okay, so
so-
it's strictly separable. So but it's clear now?
Yeah.
So they are.
Both of these are strictly bigger or smaller, they should be bigger. But if this somewhere equal 0, this should be 0.
Okay, so the point is now it's clear it cannot be 0.
All are strictly bigger
Yeah.
or smaller.
I miss you. You want drinking or silence?
Another question is about the definition of the H&M. So if this definition makes the H&M a closed set.
No, they can. It can be anything. Yeah, it's just finite. You have
You mean all H&M's finite points?
finite
Yeah.
sets of points.
If finite points, it's finite points closed sets, but if finite point of
So we just say in each set H we have H different number of points, and set M we have M different number of.
a number of points.
Yes.
Oh, yeah. Not because points are closed sets.
Yes.
Yeah. Yeah. It's just.
It's a little bit nicer here with the fan, but I feel there's no fan.
And the other I think I have fever.
Really?
Yeah, because I'm coughing and I'm sweating.
Yeah. Well, hopefully you do okay. I can take over.
No, it's okay. Oh, yes, yeah.
It's like variable.
Mhm. We can go back to which level is that?
Maybe at the very beginning. Go back. So that's this line. So you add x5 and x6 here.
Yeah, it should be equal
Equal.
to make it equal. Yeah, it was not clear, I know. But we will have more slides on the factorials later, so it should be a bit. Is it clear? Okay, so let's continue. There was a question about supplementary reading material. So it is a book. It was written by Jan Smith, who invented the simplex algorithm, and it's a pretty good introduction to linear programming. It has, this is volume 1, but there's volume 2 and volume 2. Pretty big topic. So I give it to you. You can, if you got bored, you can read it, but at the end of the lecture, I want you to take a look at it. You might like it. It's pretty fun. So linear programming, it's really huge. So we will have only 2 lectures on it. But when I studied it, we had 2 semesters, and it was called Introduction to Linear Programs. Okay, so this is where we stopped, that we have this real number p, and we know that it's positive. And using that p, let me define A vector as 2 over P times C, and let B defined by as 1 over P times the minimum of C transpose X, where X is in H, plus the maximum of C transpose X again, where X is in M. So that's why it was important that the P is positive, right? Otherwise it would be difficult to divide by it. It can be 0. So this is how we define A and B. And now we just need to prove that this A and B will be good for us to have these properties here. Definition of A and B is clear. I cannot see here. Okay. And now what we have is that the minimum of this C transpose X, X is in H. Oops. Let me start differently. So let's calculate the minimum of A transpose X. So what is what we need to prove? That, just to remind you that your M is this. Right? We want to prove that this minimum of A transpose X okay, I was wrong. I missed H and M. So let's. So I need to prove that the minimum of A transpose H is at least 1 plus B, right? So let's go there. So what's this minimum A transpose X? We just defined A. 2P C transpose X. What's the definition of minimum? What's the definition of let's do this. So let me just rewrite. So it's minimum 2 over PC transpose X. Let me divide this as minimum 1 over P, and I just write it C transpose X plus C transpose X. One over P minimum. Wow. I don't need to care, right? Minimum C. And I want to use the definition of P. So what was P? P was defined here. So I just write this is maximum C transpose X. X is in M plus P. Do you follow me? What I did? So we started with minimum A transpose X, X is in H, and I just used the definition of A, which was 2 over PC. I put that here, and I have these two. I just rewrite this as minimum 1 over P and C transpose X plus 3 transpose X, and for this 3 transpose X, I used the definition of P, which was defined here. So this is maximum 3 transpose X plus P. I see some here, someone sleeping. Is it clear? Good. Okay, so what we have, that this is 1 over P minimum C transpose C transpose X plus maximum C transpose X plus P and now we are in good shape, because what is this thing here? Just think of the definition of B. So what B was defined with is. So I'm a bit lazy, but whenever I just write min, of course I mean that minimum on X, and whenever I just write maximum on M. Okay? So what is this 1 over P times this? That's B, and we have P over P, that's 1. So what we proved is that minimum A transpose X, X is in H, that's B plus 1. And this is what we wanted to prove. If you think of this theorem. Right? So the minimum of this A transpose X, when X is in H, it's always at least B plus 1. And we need to do this for the other direction as well. Yes? Here. So I just want, so you can, but I want to have exactly plus 1 and minus 1.
But let's say the minimum of X H C transpose X minus B taken from that, and the smaller than plus 1, you just scale it and record that scale to the same thing minus 1 and take it back.
But then if you do that and you substitute back, you will get this plus 1.
Well,
So
when I
you,
take the maximum, it has to be bigger. So I can always find a scale such that if I scale C and B, the minimum of scale C transpose X minus scale B has to be bigger than plus 1, right? I can find the same thing for X to the other M, and you take the maximum. Okay, that's good.
yeah, but I just cannot see that that's much simpler than this. I mean, we just, so we didn't do anything complicated here either, right? Did we? But I mean, we just follow it, we just follow the steps down, right? But yeah, we constructed A and B from C, and it was just one line, the definition, right? That's all. There are many other ways to do it. Is it clear? Okay. So for the other direction, we just you just do the same thing that we did. The details are in the slides. You can check at home. Okay, but let's move on. So you can prove that the maximum of A transpose X will be B minus 1. So now this is what we have is so we prove that A transpose X, when X is in H, it's always at least B plus 1, and when X is in M, it's maximum B minus 1. And this is how this can be demonstrated. So we have equations A transpose X is B, and this is A transpose X is B plus 1, and this is A transpose X is B minus 1, and it separates these two classes. Okay, and after this, then here is a linear program that we can prove that separates the classes. So we have these sets H and M, and our variables will be Y and Z. They will be like error terms. Y is in the H dimensional Euclidean space, so we have H number of points, lowercase h, and Z is in the M dimensional, lowercase m dimensional Euclidean space. For each point here, we have Zi. Remember? We want to find A and B such that these are the constraints. So it looks a bit complicated, but actually it's very simple. So we want to minimize 1 over H times the sum of y's plus 1 over m times the sum of z's. So these are like errors. They will be non-negative. So we have yi is always non-negative, zj is always non-negative. And we have these other constraints that yi is always bigger than minus a transpose h plus b plus 1 in the H group, and of course Dj is always bigger than A transpose Mj minus B plus 1 in the other group, the M group. Okay, and now the theorem is that H and M are linearly separable if and only if the optimal value of this linear program is 0. So we have a classification problem, and then we could rewrite the classification problem as a linear program. Is the linear program clear, the definition? Clear? And theorem 2, if H and M are linearly separable and y star, z star, a star, b star is an optimal value of this linear program, then f of x, a star transpose x plus b star is a separating hyperplane. Yes? Yeah. So first just think of, so it's clear that it's a linear program. And second question is why this linear program is any relation to our So we need to prove these two theorems, and then we will see that we can do related to our the theorems are clear. So if I prove this theorem that answers your question by this linear program related to the So if they are linearly separable, we need to prove that then y star and z star is 0. So this is the linear program. Okay, this is here. And you can see that y and z, they are always non-negative. So this cost function, it can be never negative, right? What happens when this cost function is 0? It means that all the zj and yi, they are zeros. And it means that, say, 0 is always bigger or equal than A transpose mg minus b plus 1 in the M group. And we also have that this one, that yi is always, so if it's 0, then 0 is always bigger or equal than minus A transpose h plus b plus 1 in the H group. And this is what we proved, that class is linearly separable if and only if these two is true with zeros. Right, so this is what we can see. So optimal value of LP is 0 when, if and only if, phi star is 0, Z star is 0, and right, we know that. And in that case, A transpose HI is bigger than B star plus 1 for all I 1 to H. And we also have that A transpose M I less or equal than B star minus 1 for all j in the M group. And now you use the previous theorem that we just proved. This one. H and M are linearly separable if and only if there is existent A and B such that this holds. And the linear program says that if the solution of that linear program is 0, then the solution has these properties. Is it clear now? So it's just think of this as error when you make a mistake in the classification. When you make a classification, when you make a mistake in the classification, then this phi I would be negative, or this j would be negative. Yes, it's another error. And we want to minimize that. If that error is 0, then we classify. Okay. So now we have a linear program. We can for classification. You can use this for classification. What can be the properties of this? When you use properties? So if you factor the maximum margin classifier, can it create the maximum margin classifier? Maybe not. That it doesn't care about margin. Just cares about that one new classification. So if the two classes are linear separable, then the cost function is 0 on the left. Okay. And this use this linear program, this classification system is used in real programs as well. So for example, the University of Wisconsin, they use this method to do breast cancer diagnosis. So what they do is that they sample some fluid samples from breast, and they trace these samples on glass and stain to highlight the nuclei of cells. Then they take images of these samples, and then you use this linear classification system to separate the two classes. Where the two classes are, so we have two classes. One class is benign plants and the other is malignant. The two of us separated. And they got 97.5 linear. Because with value pattern, usually linear programs are simple. We can solve larger. So I think it's sort of, you have to solve larger programs that are if you have you put some values, put in linear classification, in here it's not enough. So maybe you can so it's not scalar, it's just linear. So you do that so no, I cannot say balance other than okay? That's good.
Does it have any advantage over linear distributions on other things? Like LDA?
So LD, they have this assumption that the sample set looks like Gaussian, right? Sometimes you don't use that, but LD might work as well. It's a different approach.
Something similar like in WLP?
Yeah, so again, it's computational. Okay, so usually depend. Yeah, so it's usually it's very fast to solve LP problems, but you might have difficulties with LP as well. So it really depends on the linear problem. So you can try those algorithms. It's probably just computational issue. Otherwise, so what happens if not, then you could do this detect that with Y stars, B stars, they would not be negative. You would see some error. Okay, so let's move on. And let's discuss the standard form, canonical forms, and inequality form of linear programs. And then we will see how to transform linear programs, and we will discuss the so-called pivot transformation that will be very crucial for the simplex algorithm. Okay, so we already discussed this actually, that this is what's called the inequality form of linear programs using matrix notation, that we want to minimize or maximize the cost function C transpose X that is in the n-dimensional Euclidean space. We have some linear constraint A transpose X is not bigger than B, and X vector is between L vector and U vector, where the between is a coordinate-wise ordering. Okay, so this is the inequality form, and the standard form of linear programs, they is that we want to minimize. So in standard form, we always want to minimize C transpose X, where again C is in the n-dimensional Euclidean space, such that A times X is B. So it's strict. So it's not inequality, it's equation. And we have this other constant, that X is non-negative. And sometimes people also require, but it's not always the case, that the vector B is non-negative as well. Is it clear what we mean on standard form of LP? And the theorem that we have is that any linear program from that form can be rewritten to this form. How trivial is this? Not true? Not at all. So if it's a midterm question, then you would come out of the room, or you could prove it in the session. Okay, so let's see. So how can we, so remember this is the inequality form. How can we get rid of the inequalities? So for example, if I have x1 plus x2 less than 4, or not bigger than 4, then I can just rewrite this as this, that using slack variables, right? x1 plus x2 plus x3 is 4, where I have this other constraint that x3 is non-negative. Right? By the way, if you could do the opposite too, if at some point you want in your life that, say if you have a equation, then it's equivalent to this. x1 plus x2 is not smaller than 4 and not bigger than 4. So you could rewrite equations in equality design. Okay, so how can we get rid of negative variables? So here we have this very strict condition that all the variables, they have to be non-negative. But in the original form, we just had some bounds, right? So what can we do when we have negative variables? Or so what can we do if, say, in the original problem we had this, that x is a real number. What should I do with this to rewrite the linear program with non-negative variables? So I want to everything to keep linear. So I don't want to use absolute values and so on. Yeah, So that's a simpler. That let me just write that x is say u minus v, where u is real, v is real. Okay. Okay. I just didn't want to say absolute value. Okay. Yes, exactly. Oops. Good point. Yeah, that was the goal, right? So okay, how can we get rid of bounded variables? So for example, if I have x is in 2 and 5, well, I can just add this to A and to the matrix A. Taiwan. Okay, if I have this to calculate maximum C transpose X, but I can solve only minimization problems, that one what can I do? Okay, and what can I do if in the vector B a component is negative? How can I make it non-negative? Yeah, so if I just multiply that row of matrix A with -1, right? I rewrite the whole thing to equations, and then I can just multiply both sides with -1 in that row. So AI transpose X is BI if and only if minus AI transpose X is minus BI. Okay, so if you just use these sets, then that proves this. So the lesson is from now on, we will focus on these kind of problems. Is it okay? You will be happy? You are not saying I was cheating because we didn't consider all linear problems. So this is an important step. Are you happy with this? Good. Yeah, I think I should stop soon. This is my alarm clock says that. So if we have a system in an inequality form, then it's just an example, and I want to rewrite this into standard form, then we can use those steps. Say I can add these X variables, and we got what we needed. Let me skip just this. And in the last minute, I just want to mention this very important transformation. It's called pivot transformation. Have you ever heard about this? Who have heard about that? Who haven't? Very good. So what we do here is that we choose this is the original problem. We choose a non-zero element in this matrix A. So say, for example, I can see that the multiplier of x for is 3. 3 is non-zero. I choose that. And I'm saying that I'm going to make a pivot there, which means that I want to modify the coefficients of this to 1, and I want to use this equation to cancel x4 from the other equations. So we will divide these equations by 3, and then subtract this equation from this and this, and that eliminates x4 from the other equation. Okay, so we will continue with this next Tuesday, and then hopefully we can finish simplex method. So if you have questions, then just come to my office hours.